Hey, everybody. Welcome to class. It is Tuesday, the 14th of October. I hope that you enjoyed your weekend. We are going to be jumping back into our discussion of sugars. Now, I've got this slide deck up, and I'm going to go full screen on this and share my screen. Okay. So one of the things that we talked about last time with respect to sugars was we talked about terminology, and we brought up that terminology because that's pretty important when it comes to like distinguishing between different sugars. For example, we talked about the number of carbons and how that influences prefixes that are used. For example, what we've got right here is an example of a triose. It has a total of three carbons. And one of the last things that we mentioned on Thursday before I had to abruptly leave was we talked about carbon chirality. Now, could you add to the chat how many chiral carbons does this carbon right here have? One. Perfect. Because this is bound to three different things, and this is bound to three different things, though it's bound to four things total. So our chiral carbon here in a triose is one. Now, as you get into something like a hexose, specifically an aldohexose, you can see that there are as many as one, two, three, four chiral carbons. Now, when we talk about sugars, we talk about aldoses versus ketoses, and pretty much everything that we've looked at this point in the slide deck is we've looked at nothing but aldoses. Now, with that, the next thing that I want you guys to be able to do is use that information regarding an aldose or ketose. For example, here's what we have is on the left-hand side, we have an aldose, and on the right-hand side, we have a ketose. Now, these two sugars, well, if you look at the different carbons, okay, so here's our ketone functional group, and then we've got, okay, so this would be carbon one, two, three, four, five, and six. Now, the positioning of the hydroxide groups on carbons number three through five, those are basically identical among these two sugars. And so that's one thing that's worth noting is that these two specific sugars are commonly referenced as being similar to one another. On the left-hand side, we have glucose, and glucose is one of the sugars that we're going to highlight and focus on more than any other sugar. But if you were to, if you were asked to draw the ketone form of glucose, it's this right here. And the reason that I say it's this right here is because carbons number one and two on your ketose are basically a wash, whereas carbons number three, four, and five, the positioning of your hydroxide group on the left-hand side on carbon three, right-hand side for carbon four, and right-hand side for carbon five, that is almost identical to three, four, and five. Now, could everyone give me a one in the chat if they follow that, and then give me a nine in the chat if they're like, could you say that again? Could you explain that again? Okay. So now, with that information or with that said, I am going to give you guys a poll question, and that poll question is seen in just one moment. It's on the next slide. I'm going to save this, and then I'm going to activate this poll question, launch. Okay, so looking at this question, which of these sugars is an aldose? Is it A on the left-hand side or B on the right-hand side? An aldose is going to have an aldehyde functional group. And these are the exact same sugars that I was just showing in the previous slide. So the correct answer for this, whenever you're looking for an aldehyde functional group, you're looking for a carbonyl carbon. So here's our carbonyl carbon, and then a hydrogen, and then an R group. R being the organic chemist. So yeah, we just I mean, it's anything's in our group. Everything's in our group. So this is a carbonyl, H, and then an R group. There's your aldehyde functional group. So we're looking at A as our correct answer for that. We got about 78% of the class who responded with that. So there's our aldose, and there's our aldehyde functional group. I'm going to end that poll. We've got some more poll questions today, though. So there is our aldehyde functional group, and there is our aldose. Um, we've got our ketose on the right-hand side. They both have a carbonyl carbon, and it's just a matter of what is that carbonyl carbon bound to? Is it bound to a primary alcohol and then an R group, or is it bound to an R group and a hydrogen? Okay. Now, another thing that is important, kind of your next level. So if you want to recount, like, what are the things that we know about sugars at this point in time? I'm going to take an inventory of them. One, is it our prefix ose? So how many carbons? Number of carbons. Second, aldehyde. There's that. Aldehyde versus ketone. And these two things can be combined. So on the left-hand side, that's an aldehyde, so that's an aldose. And it has 3 carbons. So we call this an aldo triose. And this sugar right here is also, oh, I'm sorry, I just saw that. What the slide deck that we were looking at is titled Week 7, Day 1 Sugars. So Week 7, Day 1 Sugars. Okay, so we've got an aldotriose. This also is an aldotriose. I like talking about sugars because I feel like it's a hierarchy. We're building on this information. Now, with that in mind, these two sugars, I want you to look at them and I want you to say, hey, they're different. These are different. They're similarities, but there are differences to them. And the difference is in the chiral carbon. So the question is, what does the chiral carbon have on it and where is it positioned? So the chiral carbon in both of these sugars has a hydroxide group and simply a hydrogen. The hydroxide group on this molecule is on the left-hand side of our molecule. The hydroxide group on our other molecule right here is on the right-hand side of our molecule. So that is where we are able to identify and distinguish between these two sugars. The one that's got a hydroxide group on the left-hand side, this is known as an L sugar. The other sugar is a D sugar. If you remember R and S in organic chemistry, you might also remember D and L forms of molecules. There's dextrorotary or dextrorotary and levorotary. And it's basically how does this molecule respond to polarized light? So on the left-hand side, we've got an L aldotriose, and on the right-hand side, we've got D aldotriose. Now, these two sugars are mirror images of one another. So here what we have is, let's see, this right here. We've got, let's go ahead and work through this. This is an aldose. Now, the question is, because when we look at all these hydroxide groups, there's one on the right, one on the left, right, right. Okay. There's 4 chiral carbons. What we want to figure out is what is the highest numbered chiral carbon. And the highest numbered chiral carbon in this is, there's carbon 1, 2, 3, 4, 5. This carbon number 5 is our highest numbered chiral carbon. That is going to be what we look for to identify as a sugar, a D sugar or an L sugar. So in both cases, carbon number 5. We look at carbon number 5 in a aldohexose, or you could rephrase it as I look at my highest numbered chiral carbon, and then you say, okay, where is the OH? Is it on the right or the left-hand side? Here we've got our OH on the right-hand side of our molecule. Therefore, this is a D sugar on the left. So this is a D sugar, sugar, and then this is an L sugar. So these are both aldohexoses, but this one is a D aldohexose, and this is an L aldohexose. Now, the positioning of our hydroxide groups, they all tell a different story. Your highest numbered chiral carbon, highest numbered chiral carbon, says D versus L. Okay. Now, what about all of the others? Well, the positioning of all these hydroxide groups, whether it's on the right or the left, all of those are going to be, are we talking about glucose, or what is the common name for these molecules? Now, what I want you guys to do is I want you to look at these linear forms of these sugars. And I want you to say, all right, well, to identify glucose, which both of these are glucose, this is L-glucose, and this is D-glucose. Both of these are glucose molecules. This molecule is D-glucose. What I want you guys to be able to do is I want you to be able to identify the linear form of D-glucose. Now, the way that I think is an easy way to remember it is to think, where are my hydroxide groups? Do I care about carbon number 1 when it comes to identifying glucose? Not really. All that I care about for carbon number 1 is I care about looking at it and saying, aha, well, it's an aldose. Therefore, it's possible that I'm looking at glucose. Now, what I'm then going to do is I'm going to look at carbons 2, 3, and 4. And if I see my hydroxide groups with the following pattern, right, left, right, then I'm going to think, okay, well, I'm probably talking about glucose, because hydroxide group on the right, then the left, then the right, and then my carbon number 5, well, that is going to designate it as a D sugar. So D-glucose. If you're trying to think of or what I would recommend as your kind of process, is the sugar D-glucose? Your first point to look at is C1 an aldehyde? So we'll go process, or we'll look through this. And I'm referencing glucose just because of the biological significance of glucose. Next step is I'm referencing, and I want you to know D-glucose because, again, the biological significance of D-glucose. And I'll get into that in a little bit. But is carbon number 1 an aldehyde? Yes, it is. Okay. So then question number 2 reads, do I have 6 carbons? If the answer to that is yes, okay. Well, now what I'm talking about is I've got an aldohexose. Okay. The next point that I'm going to do is question number 3. Does C5, carbon number 5, have OH on right? The answer to that is yes. Now you have a D-aldohexose. Okay, Now, my next question for you is, and I'd like to see you guys' response in the chat. How many carbons of our total of six have we accounted for here? Okay, two, two, great. Now, I'm seeing lots of people respond with two. I would actually take it one step farther, and I would say that we've also kind of accounted for carbon number six. The reason that I would say that is because, well, when we looked at carbon number five, part of the implication was that that is the highest numbered chiral carbon. Can you give me a Y or an N to the chat if that makes sense, or if you want me to reword that? Okay. So what I'm getting at is, the question is, so does C5 have an OH on the right or left-hand side? I'm looking specifically at C5 because whenever I look at this structure, this whole thing, I want to look at my highest numbered chiral carbon. So another way of looking at this is you could say, question number one, is C1 an aldehyde? And then next question is, what's my highest numbered chiral carbon? And as soon as I do that, I could say, okay, well, my highest numbered chiral carbon is carbon number five. Therefore, carbon number six is not a chiral carbon. So, but we've gone through these questions. So essentially what we're worried about is, well, at this point in time, I'm only worried about carbons two, three, and four. And I have that pattern of right, left, right. And are my OH groups RLR? That's my question. And as soon as I can answer yes to that, then I say, okay, well, this is D glucose. So first question is, do I have an aldehyde? Or sorry, what I'm trying to do is I'm trying to say, is the sugar that I'm looking at, is it D glucose? Is carbon number one an aldehyde? Yes, it is. Do I have six carbons? Yes, I do. Does carbon number five have an OH on the right-hand side? Yes, I do. So therefore, I know it's a D-aldohexose. Then these carbons right here are the only ones that I care about. Is it right, left, right? If the answer is yes, then I have D-glucose. If the answer is no, then I've got something else. Okay. Now, could you give me a five in the chat if you follow that? And any letter in the chat if you say, wait, wait, wait. Okay, so now what I'm going to do is I'm going to look at this other sugar that is a mirror image. Okay, this is an L sugar. This is L glucose. The important thing about the difference between a D sugar and an L sugar is they are mirror images. So if I were to look at this structure, I'd say, okay, carbon number one is an aldehyde. Carbon number five is my highest numbered chiral carbon. Well, this has my hydroxide group on the left. Okay, therefore I'm dealing with an L sugar. Can you give me a Y or N in the chat if you followed that so far? I've looked at the aldehyde and I've looked at identifying it as an L sugar. Okay. So then the next thing is I've got to look at carbons two, three, and four. Again, I'm not really worried about carbon number six, but I'm looking at carbons two, three, and four. Well, this is left, right, left. Oh, but that's backwards. You're right. Because an L sugar is backwards or the opposite of a D sugar. Can you give me a Y or an N in the chat if you followed that connection between a D sugar and an L sugar? Okay. Now, I bring this up because one of the things that I've seen over the years is that some folks will look at a structure of a D sugar, and then I'll say, okay, now could you draw the L version of that? And what they'll do is they'll take this OH group and they'll put it on the opposite side. And they'll say, there we go, I'm done. The thing is, when they do that, they haven't changed any of the other OH groups. So essentially what they did was they made an L sugar that was different at each one of those different at carbons 2, 3, and 4. Okay, so it's important to remember that a D sugar and an L sugar are mirror images of one another. Their positioning of their OH groups are going to be exact opposite of one another. Now, when it comes to an aldose, we don't have to worry about carbons number 1 and carbon number 6 because they're not chiral carbons. Whereas carbons 2 through 5, we do have to account for those. Now, here what we have are D sugars, and these two sugars are enantiomers of one another. So this is D glucose and L glucose. They are enantiomers. That's another term that we can use for distinguishing between a D sugar and an L sugar. Now, these two sugars right here, okay, on the left-hand side, I've got D glucose. A Y or an N to the chat. Does this sugar right here that I've drawn a circle star thing on, is that a D sugar or an L sugar? Add a D or an L to the chat if this is a D sugar. You're right. It is indeed a D sugar because I looked at my hydroxide group on my highest numbered chiral carbon and said, okay, there we go. It's a D sugar. Now, the difference between these is carbon number 2. Well, those are the same. Carbon number 3, the positioning of the OH groups are opposite. So I'll say oppo. I'll just say op. Carbon number 4. Oh, well, OH is on the right on this molecule, and then it's on the left on this. So these two are opposites. So tell me in the chat, how many positions do you have, well, OH groups on different sides of the molecule? 2. You're absolutely right. Carbons number 3 and 4. These two sugars are not mirror images of one another because of those differences. They are different from one another. And the best term to use to apply to those is they are diastereomers. Now, some of these terms might come back a little bit from organic, or they might be a little bit familiar, but the way that I always kind of think about this is di, okay? 2 or more diff. 2 or more different stereocenters. Okay, now what we have is D sugars versus L sugars. They are mirror images of one another. Diastereomers, not mirror images of one another, and you've got differences. Now, what about this right here? Okay, so on the left-hand side, we have D glucose. Compare these two structures and tell me how many carbon numbers or how many carbons have hydroxide groups on different sides of the molecule. Tell me the number of differences, basically. Okay, so we'll go through these. We've got, yeah, that's the same. Carbon number 2, those are identical. Carbon number 3, those are identical. Give me a Y or N in the chat if you agree so far that those are identical. Okay. Then we got carbon number 4. I'm going to put a box around that, a box around this. Okay, so we've got a hydroxide group on the right versus on the left. Okay, so those are different. So that's a different position. Then carbon number 5 right here. We got OH on the right and OH on the right. Okay, and then this last one, that's identical. So how many hydroxide groups are on different sides, but when you compare these two molecules to one another? Just one. Oofda. So we have only one hydroxide group difference. So Y or N to the chat, is this glucose? I'll ask that. The hydroxide group positions matter. No, it's not glucose. Okay. Follow-up question. Is it a D sugar? Is this molecule on the right-hand side, is it a D sugar? It is. Now, we kind of arrived at, yeah, there is one difference, and that is at, well, carbon number one, two, three, four. One, two, three, and four. Okay, so would you agree with me that these two, a way to distinguish between these two molecules is looking at carbon number four? Add a Y or an N to the chat. Great. These are what are known as, well, they are not mirror images, so no, cross that out. These are what are known as C4 epimers. An epimer is a unique term to describe sugars that are related or similar in structure to one another, but they only have one difference. So here, this is an example of a C4 epimer. Now, I'm going to draw another structure. I'm going to use a white pen, and I want you to tell me, how is this sugar related to glucose? So your comparison is to this right here. I've got 1, 2, 3, OH, 4, 5, 6. Okay. Um, and let's build this out. So this is a D-aldohexose. That's all that you have right now. Then what I'm going to do is I'm going to go to, let's say, OH, H. And then last but not least, I'm going to go up here. Tell me how this sugar right here relates to glucose. Give me the simplest and best description of what that is compared to glucose. It's not a mirror image. And I want you to use this terminology. Yeah, it's an epimer, but give me a little bit more information. What other information do we have? Perfect. This is the C2 epimer of glucose. So when you see sugars that differ by two or more OH groups, the word that we use for those is we call them diastereomers. When you see only one difference, we call those epimers. Does everyone follow that so far? Add a Y or an N to the chat. Okay. And if at any point there's a term that we encounter that you're like, I don't follow that one, please don't hesitate to send me a private message. I can circle back on it and I can talk about it a little bit more. Okay. So our next point is I want you to know the difference. I want you to know the structure of glucose, but I also want you to focus in on one specific epimer, and that is galactose. I want you to know that galactose is the C4 epimer of glucose. So carbon's number 2, they both have hydroxide group on the right-hand side. Carbon number 3, they both have hydroxide on the left. Carbon number 4, aha, that's where we have our difference, our conflict, whatever you want to call it. Carbon number 5, they both have hydroxide on the right-hand side. Okay. So I want you to specifically, glucose is a structure that I want you to specifically know. And then I also want you to know how easy it is, and I want you to appreciate kind of how easy it is to go from glucose to galactose if you know that it's a C4 epimer. And the reason for that is I might give you a question that is like, hey, I'll give you a structure and I'll say, what term best describes this? Or what's the word that best describes this? And let's say that I gave you this and I said, best descriptor. Okay, I got a private message question. How is glucose related to D-aldohexose? Well, glucose has, to answer that question, here's glucose on the left-hand side. Glucose, just a second, I'm switching to a different, there we go. Glucose is, this is the common name for this molecule on the left is glucose. It has an aldehyde. Therefore, it's an aldose. It also has one, two, three, four, five, six. Has six carbons. Therefore, glucose is an example of a D-aldohexose. So another way of putting that is an aldohexose is kind of a big umbrella term. So you could think about it like this, hierarchy, or I always like to think about it as a hierarchy of sorts. Hexoses. Hexoses can be aldose or ketoses. Okay. Aldoses and ketoses can be D or L. Ketoses can be D or L. Now, in both of these cases, you've also got, well, sorry. You then have a list of possible kind of sugars. We've got glucose, you got galactose, you've got eulose, and I haven't shown you all these. I'm going to in just a moment, but I just want you to understand that glucose is an example of a D-aldohexose. You could also say glucose is an example of a hexose. Person who asked me that question, does that make sense? Great. Okay, so here is our display of all of the different permutations or all of the different ways that you can position hydroxide groups on a aldose. Here what we have are all of the ways or all of the possible aldotrioses right here. Here's the two aldotetroses. Four carbons, four carbons. Here's all your aldopentoses and all of your aldohexoses. Now, the ones that I want you to know the structure of and to be able to recall the structure of these, I want you to know D-glyceraldehyde, D-ribose, D-galactose, D-mannose, and D-glucose. Now, let me tell you what I recommend when it comes to knowing these. First and foremost, I start with glucose because when I know the structure of glucose, I then know the structure of mannose and galactose. How do I know the structure of mannose and galactose? Okay, well, let's look at this. I don't care about carbon 1. I don't care about carbon 6. I don't care about carbon 5. And I'm going to go ahead and cross these out in galactose as well. Can you give me a Y or an N in the chat if you follow why I crossed those out and narrowed it down to just carbons 2 through 4? Wonderful. Okay. Now I've got my mnemonic or I've got my pattern for glucose. Right, left, right. I'm going to look at mannose. And what I see about mannose is the difference between glucose and mannose. Boom. Carbon number 2. The next thing that I'm going to do is I'm going to compare the structure of glucose and galactose. And what I'm going to see there is that, well, carbon number 2 has a hydroxide group on the right-hand side for glucose. It's got a hydroxide on the right-hand side for galactose. 3 is on the left. 3 is on the left. 4 is on the right, and 4 is on the left. So what I can say from this is that mannose is the C2 epimer. I'm going to leave it as C2EP. C2 epimer of glucose. Then I say galactose is the C4 epimer of glucose. Can you add a Y or an N to the chat if you follow that? Okay, so by learning one structure, well, then you've got two structures figured out, two additional. What was the term for more than one difference? That would be our diastereomers. Mm, They're diastereomers. There we go. So I'm happy that you asked that, Lauren, because if I were to compare, and I'm going to erase some of this, if I were to compare, let's look at glucose, and I'm going to cross out, well, I'll cross out carbons one, and I'm going to scribble out one, five, and six. Got glucose, I've got right, left, right. If I were to compare, yeah, let's compare glucose to talose, D-talose at the far end here. Um, would it be appropriate, Y or N, to use the term epimer to describe the relationship between glucose and talose, Y or N? An epimer is reserved for one difference. So if we were to say glucose and talose are related, we wouldn't say, oh, talose is the C2, C3, C4 epimer of glucose. We wouldn't say that. That would be, you would essentially just say, well, these two are diastereomers. They're non-mirror images of one another. So that's why if you know glucose and mannose and galactose, I mean, those are kind of your best ones to know. Is there another epimer of glucose that's not C2 or C4? Yeah, there is. Can anyone find and add to the chat what is the C3 epimer of allose? Dang it. I'm guessing that you probably see what my mistake was. The C3 epimer of glucose is allose. Carbon number two, carbon number two, carbon number four, carbon number four. The only difference, carbon number three on the right-hand side versus the left-hand side. Does everyone see that? Add a Y or an N to the chat. Great. But the reason that I don't want you to be like, oh, I got to learn the structure of allose is again, the biological relevance. Mannose and galactose are a little bit more relevant to biology. Okay. So then ribose, I think that it's helpful to ribose or to know the structure of ribose by just looking at it and saying, okay, this is a five carbon molecule, and all my hydroxides are on the right-hand side. Done. Glyceraldehyde, well, D-glyceraldehyde, there is only one chiral carbon. This hydroxide group could only be on the right-hand side. If it's on the left-hand side, add a Y or an N to the chat. If my hydroxide is on the left-hand side of glyceraldehyde, is it still a D sugar? It's not. That would be L-glyceraldehyde. Okay, now we've got a poll question on our next slide. And it is going to pop up in just a second here. Done. Okay, so what term best describes the relationship between these sugars? We've got carbon number. Don't care about this one. Don't care about this one. This one. This one. Don't care about that. Don't care about that. Okay, so I've really got, carbon number two. Those are identical. Carbon number three. Those are identical. Carbon number four, however, that would be our place where we have a little bit of a distinction and where we have a difference. So I'm going to put a check mark by two and by three, but four is the one that is kind of the oddball. So that's why these two sugars, maltose and idose, are epimers. Now, with that in mind, is this the sort of question you might see on an exam? Yeah. Did you have to know the structure of maltose to answer this question correctly? Give me a Y or an N to the chat. No, you don't. I mean, I gave you the two structures and I asked, well, how are these two related? Are they enantiomers? Are they diastereomers? Are they epimers? Or none of these are correct. Well, you did not have to recall the structure of maltose or idose. You just had to look at it and say, okay, well, What are similar? What are different? And the correct answer here is an epimer. I'm going to end that poll. Okay, now here are your ketoses. For your ketoses, I want you to know the structures that have the rectangles around them. Now, let me ask you this, and please answer. Uh, are 3 carbon long structure there? Dihydroxyacetone. Should it have a D or L in front of it? Add a Y or an into the chat. No, it shouldn't, because this is not a D or L sugar. There's not a chiral carbon on here where you can position on the right or the left-hand side. So there's not that chiral carbon. There's not that OH group that you can move. So there's no, like, this is not D-dihydroxyacetone or L-dihydroxyacetone. Now, fructose, this is your molecule. Like, if we look at, let's count up our carbons. I'm going to dismiss number 6. I'm going to dismiss carbon number 5 because I know that I'm talking about a D sugar. Carbon number 1 and 2, those are consumed as a part of my functional group. So carbons number 3 and 4. Would you agree with me that our hydroxide groups are positioned in an LR pattern? That's why fructose is commonly referred to as the um, ketose version of glucose. Because carbon number 2 isn't on, or doesn't have a hydroxide group, but carbons number 3 and carbon number 4 match the pattern, the left-right, of the right-left-right that glucose has. Okay, here we've got another poll question. What terms best describes the relationship between these? Okay, and we can kind of go through the same thing. Don't care about this, this, this. I don't want to sound nihilist or nihilistic. I don't care about that. But it doesn't come into making our decision. Ultimately, carbons number 3 and 4 and the hydroxide groups positioned on those carbons are what are going to influence our terminology. These are both D sugars. And I'm watching as there's kind of a quiet battle taking place. And if we look, carbon number 3 has a hydroxide group on the right-hand side. Carbon number 4 is on the left-hand side. Carbon or 3, in our other sugar, it's on the left-hand side. Carbon number 4, it's on the left-hand side for both of them. So the only difference is carbon number 3. So the difference between an epimer and a diastereomer is how many hydroxide or how many positions are different. So if we look back right here, what we want to do and what we are interested in, and I'm going to end the poll question. What we want to do when we look at sugars is we want to find out where the hydroxide groups are. And could everyone give me a 7 in the chat if they follow that this is what I'm referring to as the left-hand side and this is what I'm referring to on the right-hand side? Okay, I'm just looking at this linear structure straight down the middle, and I'm saying left-hand side versus the right-hand side. So if you were to look at this molecule, we would say, okay, well, carbon number 1, what does that tell us? That tells us we're talking about an aldose. Can you give me a 9 in the chat if you follow that and you understand that? Okay. Now carbon number, let's see, 6, CH2OH. Carbon number 6 doesn't tell us much beyond the fact that that's where our molecule concludes. It's just a hydroxyl group. It's not a chiral carbon. So that tells us the number of carbons that we have. Counting from our functional group here, carbon 1, all the way up to here, we get, okay, we've got 6 carbons. Could you give me a W in the chat if you follow that? Okay. Now, based on those two things, we know that we are talking about an aldohexose. Give me a Z in the chat if you follow that. Now, the next thing that we're going to do with that information is we're going to say, all right, well, what else do we gather? What's how can we paint with a broad brush? And what we can do is we can look at our highest numbered chiral carbon. And the numbering goes from 1 all the way up to 6. Our highest numbered carbon doesn't tell us anything. That's carbon 6. But what about our highest numbered chiral carbon? Well, carbon number 2 is a chiral carbon. So 3 is a chiral carbon. 4 is a chiral carbon. 5 is a chiral carbon. So carbon number 5 is our highest numbered chiral carbon. And we want to look at that. And based on that, could everyone tell me the letter in the, use the chat function and tell me the letter to distinguish, or what type of sugar is this? What letter are you going to put in? Is this a D sugar, an L sugar, an R sugar, a B sugar? Add that to the chat. This one that I've been drawing on, I'm going to scribble this out. This one is specifically a D sugar. So that's based on carbons number 1, 5, and 6, we can conclude this is a D aldohexose. Can you give me an R in the chat if you follow that? Okay. Now, that gives us, okay, so we built this name up, D aldohexose, because this hydroxide group on carbon number 5, our highest numbered chiral carbon, is on the right-hand side of our molecule. Now we've got carbons 2, 3, and 4. The positioning of those OH groups are going to give us information as to what is the common name of that sugar. And I'm jumping ahead because, well, if you look at allose, altrose, glucose, mannose, gulose, idose, galactose, talose, they all have a different organization of their hydroxide groups on carbons 2 through 4. Allose is right, right, right. Altrose is left, right, right. Glucose is right, left, right. Mannose is left, left, right. Gulose is right, right, left. Idose is left, right, left. Galactose is right, left, left. And talose is left, left, left. Could everyone give me an emoji in the chat if you follow that? Okay. I'm really happy that whenever I ask for an emoji, then it's like, I got to get a good one. Good job, everyone. I like those emojis. Now, with that in mind, we got those that we've all kind of organized and placed. I'm going to go back just a tad because the question was, what's a diastereomer versus an epimer? Well, we have to look at those carbons, 2, 3, and 4. 3, 4. For this molecule, we've got right, left, right. This molecule, we have right, right, left. So let's take stock. I'm going to say same, place, OH. Between these two sugars, are the hydroxide groups on carbon number 2 in the same position? Add a Y or an N to the chat. Yeah, so we're good there. Those are identical. What about carbon number 3? Are those on the same side of my molecule or of my molecules? No, so I'm going to put a frowny face there. Now, this information alone, looking at carbons number 2 and 3, that doesn't tell us the whole story, but based on this, we could say, okay, well, they're at least epimers of one another. But is that the only position that matters? Now we have to go on to carbon number 4. Carbon number 4, are they on the same side, those OH groups? No, they're not. So now, by virtue of us seeing two differences, carbons number 3 and 4, that is our kind of threshold that we need to say these are not epimers. Does everyone follow that? Give me a 0 in the chat if you follow it. These are not epimers. An epimer, or a pair of epimers, they have a difference of 1 carbon. So these are not epimers because they broke that threshold by having more than two difference, or sorry, two or more differences, which gives us that they are diastereomers. Okay, can you give me a Y or an N to the chat if you follow all of this? Okay, great. So now I'm going to go back to here. We did that. We did that poll question. Okay. So the next thing that I want you guys to be able to do, the next skill that I want you guys to be able to develop is to recognize structures. And I want you to look at them in their linear form, which is what we've looked at here. But I want you to be able to convert that to a ring form. Because if there's one thing that I learned in organic chemistry, it was that rings are somewhat stable, especially when you got a lot of electronegative groups like hydroxyl groups or polar groups like this. This right here is what's known as a Haworth projection. Now, what I want you to do is I want you to look at this bold line. And this isn't too radical of a stretch, but that bold line, just imagine that that's the, I'm going to actually put an X on the bond that is closest to you. And then I'm going to put a Z on the bond that is farthest from you. Okay. So the way that I always kind of envision this, and I know you've got your chair and your boat conformations, but I look at this as that X is like right here to my face. It's close to my face, and then the Z is back. But other than that, it's almost like I've made a six-sided table. Could you give me a Y or an N to the chat if you follow that? And I say table as like a relatively flat surface. Okay. Now, with that in mind, what I want you to do is I want you to imagine, okay, so we've got this X, that's the front of the table, the Z, that's the back of the table. I've got 6 points here. This is a 6-membered ring. Are all of these 6 members carbons? No, they're not, because we've got an oxygen right there. Now, with that to say, what I want you to do is I want you to look at this and say, okay, this is carbon number 1. This is carbon number 2, 3, 4, 5, and 6. Now, there's a lot that we're going to unpack on this slide, and that's fine. Carbon number 1 here. Let's think back to a moment. Carbon number 1 in our aldoses. That was an achiral carbon, right? That was not a chiral carbon. If I told you that there was a hydrogen right here, and this is one thing I also teach a non-science majors chemistry class, and this is always tough to like communicate to them, and they get it. It's just like, but you're breaking your own rule, and they're totally right. One of the things I remember from organic chemistry, aside from drawing lots of dots and lines and stuff, was you draw a Fisher or you draw a Lewis structure. And then at some point, I remember my organic professor saying, "Hey, don't worry about drawing all the hydrogens. Don't worry about it. They're there." And it's like, oh, I I felt good about that. That was a confidence builder for me, but respect, I won't. Okay, so with that in mind, look at the carbon 1 there and tell me, answer yes or no. Is that carbon number 1? Is that bound to 4 different things? Bound to a hydrogen, an oxygen that's within a ring, an OH group, and an R group. So it's bound to 4 different things. So this right here, this carbon number 1, is a chiral center. Okay, now with that in mind, I'm going to erase this hydrogen because, organic chemistry, we don't have to draw them. I'm going to call this carbon number 1. And now, could you tell me, or use your kind of own, you might have to toggle back and forth between this slide and a slide with the linear form of glucose. I'm about to draw it, but I just want you to be ready to do that. This is glucose. This is cyclic glucose. Now try to convert what does right, left, right in the linear form translate to in this cyclic form. Try to do that, and I'll give you a second. And whenever you're ready, if you have a kind of guideline or rule, go ahead and type it into the chat. But in the meantime, I'm going to draw glucose. 1, 2, 3. Oh, 4, 5, and 6. CH2OH. Okay. I'm seeing a really great answer. Right means down and left means up. Yeah, that's absolutely it. Because in our glucose, and you know what? I'm actually going to skip over, I'm going to give us the 6-carbon structure, and then I'm going to draw OH, OH, and OH. I'm only going to draw those hydroxide groups because carbon number 1 in a linear form, well, that's not a chiral carbon. Carbon number 5, that tells me if I'm talking about a D sugar or an L sugar. I don't really care about where it's positioned because that's like, you need to know it, but it's maybe not the most important thing. So, and sorry, you need to know it. It's not the most important thing though, because do you think, add to the chat, do you think a D sugar is more biologically significant and relevant than an L sugar? Add D for that's more important, L for that's more important. You're right. D sugars are the biologically relevant sugars between D and L sugars. Now, with that in mind, I'm so happy that I believe it was Melanie who mentioned that, oh yeah, if it's on the right-hand side, that means it's going down. If it's on the left-hand side, that means it's going up, right, down. Okay. Now, with that in mind, I want to take a little moment. Can you explain that D sugars are So I was just asked a private message question. Can you explain why D sugars are more biologically relevant? Now, short answer is the enzymes in your body that are responsible for metabolizing D sugars. If you give them a billion L sugars, they say, don't care, I can't do anything with it. If you give them a D sugar, they say, I can work with that. So the answer to the question is enzymes have preference. They have a D sugar preference over an L sugar preference. Could you draw a line to show the bond of the linear form that would make the cyclic form? I'm happy that you asked that. I was just about to do that. So I'm going to draw my carbonyl. And for the person who asked about D sugars versus L sugars biological relevance, I hope was that an adequate answer. And if it wasn't, then we're getting into that's an evolutionary biology question. That's a great question though. And yeah, so what we've got, I went ahead and drew the OH group on carbon number 5. The reason that I did it is because I'm going to circle the oxygen in my cyclic form that is the oxygen within my ring. Where is that on my linear form? So this right here is this right here. A fair question from that is, okay, well, how does that happen? Now, for a moment, let's talk about partial charges. What can you tell me about the partial charge of a carbonyl oxygen? First of all, does it have a partial charge? The oxygen within a carbonyl group. Y or an N, does it have a partial charge? It does. So I'm going back to my linear form. This right here, that has a partial charge. Do you think that's a positive or negative charge? Thinking about electronegativities and N for negative or P for positive. It's going to be a partial negative. You're absolutely right. So that group has a partial positive or partial negative charge. Each one of these hydroxyl groups also has a partial negative charge. A carbon within a carbonyl group, lo and behold, has a partial positive charge. Could everyone give me a 6 in the chat if you follow this conversation about partial charges? Okay. Now, with that in mind, I said all of these oxygens, all of these hydroxyl groups here, 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 they all have partial negative charges. I stand by that. What do we know about a partial positive charge? Well, it's going to seek out a partial negative charge. Okay, so this partial positive charge, could it go to that oxygen? Sure. If it went to that oxygen, how large of a ring would be produced? Tell me how many members that ring would be. How many members would that ring be? Well, we've got 1, 2, 3. Give me a Y or an N if you agree with that. That would make a 3-membered ring. Okay. I sense some hesitancy because people are like, yeah, I see that it would make a 3-membered ring, but 3-membered rings? A 3-membered ring with an oxygen? Man, that's going to make for an unstable ring. You're absolutely right. 3-membered rings are no good. They're frowny faces. Okay, well then, so yeah, it could do that reaction, or that could take place, but it's unlikely. This partial positive charge to this partial negative charge. Tell me how many members that ring would be. Add it to the chat. Got 1, 2, 3, 4. 4-membered rings, are they more stable than 3-membered rings? They are, but are they still kind of overall not very stable? Yeah, they aren't. They aren't very stable. Okay, so then we've got this partial positive. It goes down to here. We can make a 5-membered ring. That's more stable than a 4, but not super stable. And then last but not least, this partial positive goes to that hydroxide or that partial negative. How big would that ring be? How many members would that be? This would be 1, 2, 3, 4, 5, and then this oxygen would be member number 6. So the oxygen on carbon number 5 is the 6th member. So this right here is this oxygen. Can you give me a Y or an N to the chat if you follow that? Okay. So when we form a 6-membered ring, we've got something that's more stable. That's a favorable ring size. Now, I got a question a little bit ago, and I think it was in a private message that was, could you draw a line to show the bond on the linear form that would make the cyclic form? I hope that answers that question. I hope that was what you were going for. If you wouldn't mind confirming, yeah, that's what I was looking for. I'd really appreciate that. Now, so what we've got here in a 6-membered linear structure, we've got 4 chiral centers. When we cyclize, okay, let's talk about this. This is a chiral center. Nothing changed there. That's a chiral center. Thank you. That's a chiral center. So we got 3, and then, yep, this is still a chiral center. Oh, but what about this? That's a newly formed chiral center. So our cyclic form of glucose has a total of 5 chiral centers. That's significant. I'm going to go ahead and add new chiral center. This new chiral center it gets a unique name. This is an anomeric carbon. That's a unique name, a unique example, because what happens is this hydroxide group, since this one was like outside of the naming of glucose, this can go either down or it can go up. And the positioning of that does not change us from talking about glucose or not glucose. So carbon number 1, this anomeric carbon, is kind of a new animal that we've got to attack. Now, with that said, the takeaway from this, what I want you to get is I want you to know how to translate from a linear form to a cyclic form. Give me well, if it's on the right-hand side, it's going down, it being the OH group. Right-hand side, the OH is down. Left-hand side, the OH is up. All there is to it. Then, when it comes to, well, what group is reacting with what group? Well, our partial positive charge on our carbonyl carbon is what will react with one of the hydroxide groups. The same thing occurs when we talk about a ketose. Now, we are focused predominantly on aldoses because glucose is an aldose, and we need to know about glucose. Now, those are the things that I want you to be able to do. On the left-hand side, we have what is known as a Haworth projection. On the right-hand side is a Fisher projection. I always just say cyclic versus linear. Now, with that said, I want you to know what are the groups that are reacting to one another. They're partially charged groups. Now, how do those groups actually react? Actually, so on a scale of, let's say 1 to 5, 1 being, I'm good. Actually, 1 to 3. 1 being, I feel good about this. A 3 being, I got to start fresh. I don't know any of this. And a 2 being, I'll spend a little bit more time on it. I think I'll be all right. Okay. Okay, great. So being able to go from a linear form to a cyclic form is going to be helpful. Knowing, and what I will do often is I'll just say right, left, right, down, up, down. Now, with that said, could I draw the cyclic form of galactose? Oh boy, I could. The reason why I could is because I remember that galactose is the C4 epimer of glucose. So if I did this, and watch this, I'm going to go highlighter, and I'm going to go ink color white. Oh man, highlighter doesn't work as the ink color of white. Okay, so we got this. We're getting there. Bear with me, folks. Okay. What could it be? It's a mystery. Do, 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 do. Okay, OH. Okay. So if I were to look at this molecule right here, and actually this would be a good exam question where I'd be comparing these two and I'd say, okay, well, what's the relationship between these two sugars? Well, one's linear, one's cyclic. But then if I get down to it, I'd look at, well, carbon number 2, right, down. Okay, that's the same, effectively. Carbon number 3, left, up. It's also the same. Carbon number 4. Carbon number 4. Okay, on this structure, it's going up, and this structure, it's going down. Okay, so that's where our difference is. That means that this is the C4 epimer of this, or vice versa. And what I mean by that is you could say that this molecule is the C4 ep of galactose. Okay, now let's see, where are we? Okay, we're doing all right. So the cyclization that's taking place, we've got those partial charges that attract the groups to one another. Now, we've got to know about what those groups are. And I want you to know about these reactions. An aldehyde with a partial positive charge is going to react with an alcohol. So here's our aldehyde functional group, and here's our alcohol. It can react with any one of these alcohols. And whenever it does, we're going to form what's known as a hemiacetal. Okay, so that hemiacetal, this OR right here, that is effectively this plus the R group. So that hemiacetal is going to be, and then let's see, this carbonyl oxygen becomes this alcohol right here. I'm going to erase the other markings. But that hemiacetal is the product of an aldehyde plus an alcohol. Now, just to kind of play along with this, we have a ketone. that can do the same thing because it's kind of functionally very similar. Could anyone add to the chat? And if you guys get this right, it's just sort of a guess. So 4375. There's an exam bonus point question on this. Um, a ketone reacts with an alcohol to form what? An aldehyde for alcohol forms an hemiacetal. Ketone plus an alcohol forms a, I'll give you a hint. It's a hemi. We're looking for a hemi close. Oh, there we go. A hemiketal. Ketone plus an alcohol yields hemiketal. Okay, there you go. You're good. And there we go. There's our bonus point. Okay, this is the visual of that taking place. These are the different groups that are reacting. If you look following the hydroxide on carbon number 5, it's easier said than done, but this animation should loop. There we go. So this hydroxide, that oxygen becomes that. The carbonyl oxygen becomes the alcohol. Okay. Now, same thing goes. Ketone plus an alcohol. The one big difference is whenever we have that ketone carbonyl react with an alcohol, well, let's see. This oxygen becomes a member, or sorry, this oxygen is one member of the ring. Carbon number 2 is where we're starting. So how large is the ring that's produced? So this is carbon 1, right? Sorry. Now what I'm doing is I'm numbering the atoms. So 1, member 2, member 3, member 4, member 5, the 5th membered ring. So we have a 5-membered ring that forms typically with that. So where I'm going with that is that ketones will typically form a 5-membered ring, whereas the aldehydes will typically form a 6-membered ring. They both are capable of forming larger and smaller rings respectively, but more times than not, when we talk about glucose, glucose can form a 5-membered ring. And when it does, it forms a 5-membered or furan ring. Whereas, uh, yeah, a 5-membered ring is a puran, a furan, and a 6-membered ring is a pyran. Okay, now what I want you to also be able to do is I want you guys to be able to, if I gave you a sugar, I want you to understand what happens to it. Okay. So when we form a hemiacetal, we have a newly formed chiral carbon. That chiral carbon can react with another alcohol. And whenever that chiral carbon reacts with an alcohol, we form what's known as a glycoside. That glycoside is also known as an acetal. Now, the important thing about that is this type of bond right here. This is a glycosidic bond or a glycosidic linkage. That type of bond is particularly important when we're talking about forming polysaccharides. So, so whenever we have a, you know, multiple sugars coming together to form a polymer, we form glycosidic linkages. And that's actually where I'm going to go ahead and stop for the day. I'm glad to